Hi, in the interest of time, I'm going to give what was intended to give a lecture on Friday, like this. So, hope you enjoy it. First of all, this is where we are, and the plan for today is to look at, or for the session, is to look at the general linear model. And what we'll basically be doing is that we'll be combining both the multiple regression and the analysis of variance into one framework. So far we just use LM, but we try to do either one or the other whenever we're doing things. So let's just continue. Simple linear regression was where we came from. We had an intercept and we had a slope, and then we had an independent variable related to that slope. Perfectly fine. Wednesday we looked at one-way ANOVAs, and basically what we did there is to say, now rather than having an independent variable that was continuous, now we have a factor variable where the I denotes the level of the factor. So basically we have the average within each of the groups here. So how do we combine these two things? Well, we do what is called analysis of covariance, so that we have both continuous variables and factors as explanatory variables or independent variables, and we still keep our dependent variables as y. So what it looks like is something like this. So all of a sudden the slope may, in this case, there's one slope, but the I group gives us the alpha here, so the intercept differs for the different groups. That's the same slope. And then there is the continuous variable. So what we have here is basically a line with a fixed, or a set of lines. Say alpha has 3 levels, so we have 3 lines that are parallel, and the only difference is the intercept. So that is the interpretation. Now, how do we extend this? Well, basically what we can do is that we can extend this by having different slopes for different groups. If we go back once, that will basically mean that the beta value here should not be 1, but it should index I as well, so that we have alpha I plus beta I times xj. So for each observation, depending on which group it belongs to, we'll have different slopes. We can of course also add more factors or more independent variables, just as when we went from simple linear regression to multiple linear regression. And again, we can transform and create new dummy variables of whatever form. So there's quite a lot of flexibility and much more. That was basically the slides. Now what I would like to continue with is some R examples. The first one relates to growth of cells measured in microns, and what was done is that for different concentrations of cells and with and without glucose added, we're looking at a measure of the diameter of those cells. So in this data, the first column contains the row name, so we'll just specify that. And just getting a summary of what we have here. Well, we have the glucose, which is coded as 1 or 2, added or not added. We have concentration measurements and diameter measurements. But rather than having glucose as a numeric variable, I would rather have it as a factor. So, and I will label this factor as yes, no, to make it more clear which one is which. So now we say that we have 32 yeses and 19 nos. And let's just do a pairs plot to see what the data looks like. And I think we should just zoom in. So what we see here is that the diameter, which is what we're looking at, definitely has some relationship with the concentration, and that may also be seen that there's some glucose dependency. So, though the dependency is clearly nonlinear, when we look at this graph, we'll just try to do the linear regression model as we learned before, or I've seen before, but this time we'll take the concentration, which is a continuous variable, and multiply it with glucose to get both the individual terms and their interaction. And if we do a summary of this, what we get is, as usual, an intercept. We get a slope relative to concentration. We get what is the difference between glucose yes, which is in the intercept, and glucose no. And then what we get here is a change in slope when you go from glucose yes to glucose no. However, in this case, this interaction term down here, which is a change in slope, is not significant. So we don't have to worry so much about that right now. But let's just look at the diagnostic plots to see what we could do from here. And looking at this, well, basically we see some structure here. So there's definitely some curvature. And if you look down here, there's also definitely some departure, in particular a few values that kind of stretches everything. And the QQ plot is also having a lot of structure starting even in here to depart from normality. Not just the outer tail, as we've seen many times previously. So one typical thing also when we looked at the pairs plot, we will see that the concentration is actually spanning a quite large range. So a log transform of concentration could be a meaningful thing. And I will also, just in case we need it, log transform the diameter. And now make a new pairs plot where we can see some more stuff in here. And I will add the panel equals panel dot smooth like this. And now we see that what we're looking for is to describe the diameter. So we are looking at graphs in this line, and with the log concentration and diameter, actually things looks quite nice as opposed to what it looks like before. So let's make a new linear model where we say diameter as a function of the log concentration times glucose, which is equivalent to saying log concentration plus glucose plus the interaction. And let's do a summary of this model. Now what we see is that we have again a non-significant interaction, and also it appears that there's no effect of glucose. In this case the factor has only 2 levels, so we actually get the right conclusion from this, but it's a good idea to actually do an ANOVA test just to see what happens. Now what we see here is that actually glucose appears to be very significant, which was not the case just up here. And the reason being that the ANOVA table is actually sequential, but everything that we did with analysis of variance models was balanced, so the order did not matter. But what this does is actually first it tests a model where does it add any information to add the variable log concentration. Then, given that we include this, do we get any further improvement in the model by adding glucose? Appears so, and then adding finally log concentration times or interaction with glucose. And to see the effect of this, we could also swap the order of the terms, so have to have glucose first and then log concentration and then the interaction. This gives us just a new ANOVA table, and we can see in particular the p-value for glucose, differs. This is the smallest that we will get, so that will not test, but we'll show this again later. But note that the ANOVA table is a sequential test. So we want to get rid of the interaction. We could do it like this, or we could use update to do so. Let's look at a summary of this model, and now we see that glucose becomes significant, actually very significant. So from this it looks like we have a good model. Let's check the diagnostic plots of this. Let's get it here. As opposed to before, the departure from normality is much less. There is still some 3 observations down here, but that really doesn't change the whole picture. You can see down here nothing is anywhere near making any problems. This is fairly horizontal, and this up here, well, it's okay for the residuals of physics as well. So let's just accept this model for now, and let's see what does it actually represent. So let's plot the data, and what I've done here is to say that I plot the concentration and diameter, and the color of each dot is the numeric value of glucose, which is then either a 1 or 2. So black means plus glucose and red means minus glucose. And the coefficients from my model are these. So what we have here is the intercept when glucose is yes, because that is the reference, and then we have the slope, and then we have the change in intercept when glucose is removed. Okay, so one way of doing this is to use AB line to first use the first parameter as intercept and use the second parameter as slope. Let's try to do that. That gives us this line. And then we could also say, if I sum the first and the third variable as intercept and again use the second parameter as slope, what would I get? Color it red. So actually the fit looks quite nice, but as always, a fit is okay, but what is the likelihood of hitting a particular value? It's none. Not going to happen, so you want to have some interval as well. So what we'll do is to make a data frame to be used for prediction, and we'll take values from 9 to 13.5, pretty much spanning our range. Just get 30 points, and each of them will repeat twice, so that we can get a yes and no glucose included as well. And then we'll do the prediction just as we've always done. And what we'll do is I'll just clear the plot, and now I will add some lines for all those where glucose is yes, like this. This could be written much nicer, but as I said earlier on, sometimes you just make things work and then you take it from there. So this is the confidence interval of this line, and likewise for the glucose no. So is this a good plot? Well, since we did not add the prediction interval, we cannot say actually how the dots are, but it looks fairly good, and it's quite clear from this that we're quite confident that those two lines do not overlap. Now, this was on the log scale. Typically, when you're communicating with your original people where you got the data from, they like their scale. So instead you might go back and plot the original data again with the color indicated by the level of glucose. And what we have to do now is that all our x's should be transformed with the exponential to get back on the same scale, but all the rest of this is actually the same as just 4 lines up. So we get the confidence interval here for when glucose is added, and likewise for when glucose is absent. Again, we see a clear separation, but we also see some very pronounced nonlinearities when we get down to low concentrations. If we want to add a prediction interval as well, we'll just do the predict with a prediction interval and adding some new lines. The only difference here being that I'll have some dotted lines rather than some dashed lines, so you can see the difference. First we add them for glucose equals yes, and we see there is one observation here that sticks out, but I mean one out of these, not so many, I mean very many observations, perfectly okay. Do the same thing for the glucose no. We see that again there's 1 point, but I mean that's just how life is. And we'll notice that the prediction interval actually overlap between the glucose yes and glucose no. So if you get a point like this point in here, you cannot say whether it actually, if you didn't know, you couldn't claim which one is more likely to be. This one is more likely to be glucose no, which is true, but you could have this one down here, which is actually looks more like a glucose no than a glucose yes, so it might be a typo, or it might be just an extreme point from the glucose yes distribution. So that was one example, trying to go back and use predict also, and then transforming back to the original scale so that we can see something that is nicer. A different example is the vital capacity, which is how much air you can exhale in one. So if you inhale as much as you can, and then it's just a matter of how much you can get out in one blow. For workers in the catering industry, I'll take something from a library called ISWR, Introduction to Statistics with R. It's a book by Peter Dalgaard. If you haven't installed it already, run this line. Otherwise, just go and load the library. Now I will load the dataset called VidCap, which is the vital capacity data, just to get a summary of what is in there. You get a group variable, 1, 2, 3. We have the age of the individuals, and we have the measure of how many liters of air they can exhale. Now the group, I will recode that as a factor with grouping of, or labels of plus, I mean 10 or more years, between 0 and 10 years, or haven't worked in the catering industry. Doing a pairs plot, what we'll see that age and vital capacity, well, there's definitely, the vital capacity goes down as age goes up. Well, that happens to ordinary people as well. But the question is that more so for those that worked in the catering industry? That's the question. There are many ways of making graphs, but for now we'll just use one from Lattice package, which shows us for each of the groups how does this graph look like. The scale and everything is the same. So basically what we see is there's not so many points for those who work there for a long time, and there's quite a large control group for those who did not work in the catering industry. So this should be fairly well established, this line over here, although there are some uncertainty associated. But let's see what happens. Now we have the group label here as a factor and age, and we want the interaction as well. So we fit the model, we will do the ANOVA test, and basically what we see is that everything is significant here, including the interaction. So we got plenty of degrees of freedom left. Let's look at a summary and see what are the parameters that we get out. Now, first thing to remember is what is in the intercept. It's the group that is missing, so it's the plus 10 years. So the reference here is those who work more than 10 years in the catering industry. So the slope, or the intercept, sorry, is smaller for those who worked less years, and is even smaller for those who did not work. There is a general decrease with age for those who worked in the catering industry for 10 plus years, and the slope for those who work there for less than 10 years is the sum of those two, so it is around 0.05. And finally, for those who did not work there, it's a sum of this and that, just as we saw earlier. With factors, here it's just the slope that we're changing, so it becomes around 0.03. Now, a nice way of communicating this is to look at some graphs, but first let's just look at the diagnostic plots as we've done before. And you could say, well, maybe you could do some stuff out here, but let's just say it's not too bad, it's just a few points out here. So we'll get by for now. And just to see the effect of the order, what we do down here is to say h as the first variable rather than the grouping. So if we do the ANOVA test here, what we'll see is that h is highly significant, but having h first and then adding group does not improve anything, only when we also include the interaction. So this p-value is the same as what we saw up here, but the p-value for h, it becomes a little bit more significant, whereas the one for the grouping, which down here on its own is significant, but when you control for h, it's not significant unless you say that they also have different slopes. That's a bit confusing. The reason here is that as opposed to Wednesday, everything is not balanced anymore, so there is some more correlation, and the different parameters does depend on what else is in the model. So it's similar to multicollinearity to some extent. Okay, so compiling a nice plot, just like we did in the first example. Let's just plot the data. Looks like this. Again, I did color coding according to the grouping, and you will see that the green group are those that didn't work, the red ones are those that worked there for a period of time, and the black ones are the ones who worked there for a long time. And if we do it the same way as before, looking at the coefficients, let's see them. Now to do AB lines the way we did it before, well, the first one is easy because that's just using the fourth as intercept, the first as intercept and the fourth as slope. Now the second line, you need to take the sum of these two to get the first intercept for this group, and you take the sum of these two to get the slope for the group of those who work less. And finally, it's a sum of the first and the third one to get the intercept, and the fourth and the sixth one to get the slope. So that is what we predict. Just adding a legend so that we can see what we're actually looking at. So this is our prediction from our model. But again, this is sort of laborious, and when things become more complicated, it becomes a mess. So it's much nicer to actually use predict in this setting as well. So how would we get about doing so? We'll see that in a short while. So let's just say that what do we actually need to predict this? Well, we need some prediction data, which should be a data frame. And what do we need in here? Well, we need something that covers the age range where we actually want to make predictions. So age, and I'll actually do this differently. I'll use expand.grid. So age should take values from 0 to 65. We could just say I want the sequence from 0 to 65 stepping 2, just showing what you get. well, we get close to 65 anyhow. We could just take the 66, and then the other variable, well, it's called F group, should be the levels of our vid cap $2 F group, like this, just to show you what you get. As expected. So now we can do the prediction of these. And now the trick is to do the prediction. And maybe I should stop this and just show you the code when I've done this, because this will probably take a short while before I get everything straightened out. But it's basically just lm1. And then we say that new data should be pred.data, and for now we'll just take an interval which is the confidence interval. So this will work fine. I'm sure. So what is int pred? Well, let's look at it. Let's just view it. So we get a fit, lower and upper bound for each of these, and when you get to around 30 you kind of restart, and we need to figure out a way to plot this. The deal is that it actually follows pred.data, so we actually should just merge these two things. So we can cbind pred.data, int.pred, and this will be our new, let's just call it data. And let's look at data to see what it looks like. So here we have the age and the corresponding group, and the fit and the lower and upper bound. So now it's just a matter of plotting, and there are different ways of doing this. Now the challenge is that we will first have, how many different ages did we do? 33, as remember, 34. 34. So n is 34 in this case. So basically what we need to do is to flip this around and do things. But let me just do it while we're at it. So for each age here I get a fit and lower and upper bound, and I can either do the first 34, the next 34 and the last 34, and do that once and for all, because if I want to do all in one go I will get some weird lines going back and forth in this here. But I can also choose to say I want this and I want to flip this whole thing into another structure and then plot that. Both ways will work. So let's just try something that works at least. The easy thing is to, we'll just type it. Math lines we want to add here, and what we want to use is pred dot, we want to use data $h. Maybe you can actually do this smarter. I'm actually not sure. Let's just look at the help page for MATLAB. Does MATLAB have a formula expression? No. So data $h and I'm just looking. We'll just try something, see what happens. And then we have, let's just take the entire thing, int.pred, to see what this does, basically what we want is to do a subset, which is 1 through 34. This is the last part I think doesn't work. That is as expected. So this is what you get if you plot everything in one go. You see you get something that is not so beautiful. So what we need to do is to do the subsetting in here. First the first 34 rows, likewise here. And in this case, what we have 3 lines. The first one should be the line type, and should be as we usually do it, 1, 2, 2, and the line width should be just 2, and line and the color should be 1. So these were the black lines. Now let's repeat this. All we have to do is to say add 34, oops, and now we change the color to a 2. We got something around the red one, and then we'll add 68 and add 68 and write a tree. So let's just plot the whole thing again by copying this plotting command down here as well. So these 4 lines will do it, and this could be written in many other ways. So basically what we see is that the green line is quite certain, the red line is less certain, and the black line is quite uncertain. And the confidence interval for the black line actually includes the red line. So there's only marginal difference between the black and the red line. So it seems like there's a continuous dependency on this. What one should also notice is that if you look at the black dots in here, well, those who work there for 10 years or more, they are 37-ish years old or older. Those who work there less than 10 years, well, they can have pretty much any age, but they're not likely to be that old. Whereas the background population spans the entire range, even from below 20 years of age. So the sampling here is not so nice, but I mean, it's also impossible to find anyone who is maybe 20 years and worked there for 10 years. That's not okay by code anymore. So that is what I wanted to say. Thank you for now. See you around. Cheers.